This is very, very, very cool. So it did work. The startup was canceled, and I am in fact dropped into a shell. And we only know that because we were able to generate these logs. If you are interested in IoT hacking or hardware reverse engineering and have not yet acquired the skill of soldering, then this video is for you. Watch this video until the end, and I am going to demonstrate a tool that you can use that is going to make your life 9 times easier. Let's go ahead and get started with the video. Over the past few years, I have managed to acquire several IoT devices. Most of these are for learning purposes. I have some pictures up of some of these boards. And what I want to show you is that if you come across an IoT device, whether it be a camera or a smart thermostat or a router, etc., and so forth, and you are looking to get hardware level access to it, then you are hoping to see something like what you see on the screen here. So right here in the center of this photo, we have 4 header pins that are sticking up out of the board. And you can see that it says UART right above those pins. So this is your UART interface on your board. It allows you to get access to the lower level firmware that is running on the board through these debugging pins. If you get your hands on a board, this is what you are hoping to see. And then from there, you can use, say, for example, a USB to TTL adapter, and you can potentially get shell access to the device over serial, making use of these debugging ports. Now, what if you don't have the header pins? So here are 2 examples of routers in which there are no header pins. You can see very clearly in the center of this board that we have pads. They are not labeled, but these pads belong to our UART debugging ports. And likewise, in this picture, which is also a router, we have the same thing. So we have 4 pads. These correspond to the UART debugging ports, and they are semi-labeled. So for example, you have this triangle or this arrow sign that is pointing to this pad, which is most likely specifying that this is your voltage or VCC pin. But it is at this point that you would typically solder header pins to these pads. Now for me, I unfortunately have yet to acquire the skill of soldering. So what do you do if you do not know how to solder? I recently acquired this tool, and this tool has quite frankly been a game changer for me when it comes to getting access to hardware. And projects that I have had sitting on the shelf for many months now, I've been able to pull down and I've been able to make progress on. The tool that I am making reference to is called a PCBite probe. Links will be in the description. I'm over here at the home page at sensepeak.com, and this is one of the main places where you can find these tools. And this is a PCBite probe. So right here you have your probe, and it gets inserted into the probe arm grip. The probe has a tip on it that is actually sharp and very small and compressible. The probe has a flexible metal arm and a powerful magnet in the base, which will allow you to easily position it to your workstation. These right here are referred to as PCB holders. I personally do not have any of these as of yet, but I do highly recommend getting them, as well as the plate underneath, because it will make things much, much easier for you. If I were to do this over again, I would have just purchased the kit that comes with everything. However, in an attempt to try to save money, I went the cheaper route. In this video, the probes that I am going to be showing you are what is seen on this page. 4 SQ10 probes with test wires. It does not come with the base plate, and it does not come with the PCB holders. While this is the actual website where you can get these products from, in actuality, I purchased them from Amazon. So I'm going to show you what that looks like, and I will be including the links in the description. And if you choose to make a purchase for any of these items from Amazon and you use my referral links, I will get a very small kickback from that, which helps to support me and my channel and what I am doing. So this is the Amazon page for the main kit. And as I said, this is not the kit that I have, but if I were to do this over again, this is definitely the kit that I would be purchasing. It's $139. And you get 4 of the probes, you get the PCB holders, and you get the base plate. This is the kit that I have, and this retails for approximately $100 right now on Amazon. And just for the sake of showing you, there is a less expensive alternative where you can purchase 2 of these probes instead of 4, and you can get that for approximately $83 off of Amazon. While I'm putting more focus in this video on the PCBite probes and the value that they add to hardware hacking and hardware reverse engineering, we are also going to be using a USB to TTL converter. The one that I'm using is this one right here. It is made by Waveshare. It retails for $14.99 on Amazon, and the link will be in the description. It comes with this foolproof connector that only goes in one way, so you have no possibility for erring on the side of how your wires get connected. It has 3 indicator lights. You can get a listing of the pinouts and the definitions of the pinouts further down on the page. So what we have right here is one of the PCBite probes before it has been assembled. This component right here is the probe arm. It consists of 3 separate components. We have the probe base, the flexible arm, and the probe arm grip. The base is magnetized, so I can use a piece of metal underneath, and that will function as my base. This right here is the probe. It has a spring-loaded tip, and what we are going to do is simply insert the probe inside of the probe arm grip. Once you have pushed it in as far as it can go, you then take the test wire. There are 4 different colors to choose from. Each test wire has a female end on both sides, and we insert the female end into the end of the probe. Each test wire also comes with 2 color-coded cable holders. That makes it very easy for us to keep all of the wires organized. And that's it. Repeat the process for the additional 3 PCBite probes. And as you can see on the other end of those test wires, we have female ends. And we are going to take 3 of these PCBite probes, and we are going to connect the ends to the USB to TTL adapter. It's going to be hard for you to see the details on the USB to TTL adapter, but I am connecting the green test wire to the ground, and I am connecting the blue test wire to the RX pin on the adapter. And finally, I am attaching the yellow test wire to the TX pin on the adapter. My first demonstration of using these PCBite probes is on this IoT camera. So I have 2 pictures pulled up of the IoT camera over here on the right. This is a very, very cheap IoT camera. In fact, I found these cameras when I moved into my apartment. They were sitting inside of a cupboard, and I put them where I put the rest of my projects that collect dust until I get to them. So we're dealing with a very inexpensive and cheaply made IoT camera. In the picture over here on the right, I have a quarter that we're using for reference to get an idea of the size. So you can see that this camera is not much bigger than a quarter after we have removed it from its case. It does have a 3.7 volt rechargeable battery, as well as a micro SD card slot. In the picture over here on the left, if you look near the center of the picture, you will see that there are 4 pads, and they are labeled. Though it's kind of hard to read the labeling, they are labeled. If I zoom into the picture a little bit, you can actually begin to make out TX and RX. And if you know anything about how the UART protocol works, you know that there exists a TX pin and an RX pin. The RX pin receives data, the TX pin transmits data. Of these 4 pads, we really only need access to 2 of them. We need to determine which one is the RX pin and which one is the TX pin. We do not need access to any voltage pins if they exist. And as far as ground, we do need access to a ground, but we can get access to that anywhere on the board. You can see that the board has the label of ground on it. Not sure if that's meant to point to this pad over here on the left side or not, but in any event, this pad on the left-hand side did end up being a ground pin, and that is the pin that I used. To determine ground, it's very simple. You just use a multimeter and you put it into continuity mode, and you will know when you have found ground, because as long as you have it in continuity mode, you will hear a sound such as this. Now, after you find ground, you need to find the RX and TX pins. While there is a more systematic approach to this, such as, for example, using the multimeter and powering the device up and measuring the levels of the voltages, I took a different approach that I feel is a little more realistic for most people, and that is simply trial and error. I know that the RX pin is going to be used to receive data, or in other words, any output that I get to the screen is going to be coming from the RX. Whereas if I want to interact with the device, that is going to be by way of the TX. So the first thing that I'm going to do after finding ground is I'm going to focus on the RX, because I want to see the output on the screen. So if I see output on the screen, I know that I have correctly determined the RX pin. After I have found the RX pin, then I'll move on to the TX pin so that I can potentially interact with the device. Spoiler alert, the RX pad is going to be this second to last one right here, and the TX pad is going to be this last pad. An important thing to note is going to be that when we are talking about RX and TX, you do have to differentiate between the RX and TX on the device and the RX and TX on the USB to TTL adapter. You can think of this like a conversation. If you and I are having a conversation, when I am speaking to you, I am transmitting data to you, and you are receiving data from me. Therefore, my TX pin is going to transmit data to your RX pin. And when you are speaking to me, you are transmitting data to me, and I'm going to receive that data on my RX pin. So the TX pin on your USB to TTL adapter is going to connect to the RX pin on the device. And the TX pin on the device is going to connect to the RX pin on your adapter. And for all intents and purposes, I'm using the words pad and pin interchangeably. First thing I'm going to do is create a directory. I'm going to use make directory for that, and I'm going to call this directory IoT. CD inside of the IoT directory. And we are going to be using a tool called Minicom. If I do apt info on Minicom, we get back that it is a friendly, menu-driven serial communication program. Minicom is basically the tool that we are going to be using to get the shell access to the device over the USB to TTL adapter. I can pull up the help menu for Minicom by typing in minicom-help. And there are going to be a few options that we are going to be using. First one is going to be the -lowercase b option for the baud rate, and we are going to give it a baud rate that is typical of most IoT devices, and that is going to be 115/200. You can think of the baud rate as the speed of the communication. If you and I were having a conversation, the baud rate would be the speed at which I am choosing to communicate my words to you. I can either talk in a speed that is more or less like the speed that I am using now, or I can use a speed that is really fast, and in that case we'd be using a baud rate that is much higher. That is the baud rate. Next option that we are going to use is going to be -D. That is going to be for the device. And we are going to determine what that is here momentarily. We are also going to use the -C option, and that is used to start a capture file. So everything that appears on the screen, we are going to basically save that to a file so we can go back and look through it line by line later on. And that's going to be it. So I'll hit Q, clear the screen. I'm going to run dmessage. I'm going to run dmessage with sudo privileges, and I'm going to use the -W option. And what that basically does is, rather than just print everything to the screen and be done, the -W will continue to print kernel messages to the screen as they come in. After plugging in the USB to TTL adapter, we will be able to see in real time through the generation of the logs where our Linux system is registering this device. So with dmessage running, I'm going to plug in the USB to TTL adapter. And immediately there is some output on the screen recognizing the device, and what we are looking for is going to come on the last line at the very end. TTY USB 0. That is going to be the location in our Linux file system where this device is being registered to and attached to. That is very important. So I will go ahead and Control C, clear the screen, and now we can use Minicom. I'm going to start up Minicom, and once that is up and running, I will power on the camera, and hopefully we will see some output on the screen. So I'll do sudo minicom -B lowercase b for the baud rate. The baud rate is going to be 115200. I'm going to do a -C for the capture file. I'm going to give the name of the capture file camera.txt, and finally we will do a -D for the device. And as we determined, the device is going to be in /dev/TTY USB 0. And hit enter. And now Minicom is set up and ready for us to go. So the next thing that we will do is power on the camera. All of my PCBite probes are connected. And as soon as I hit that power button, you are able to see output on the screen. These are equivalent to your kernel messages upon boot up of your operating system. This is very important. There's going to be very important information that is going to be in these logs. And that is why we are saving all of this to a capture file. If you are seeing output similar to this on the screen, then you can rest assured that you have correctly identified the RX pin. If you are getting a display of partial information, but maybe it's not all showing properly on the screen, then that could be an indication of you are on the right track, but you potentially have your RX and TX pins backwards. But if you see something like this, you know that your RX pin has been correctly identified and you are using it correctly. Now the next question is going to be, do we have the TX pin properly connected? Because if we do, we should be able to interact with the device, or in other words, send data over to the device from our machine. Easiest way to test that is to just hit enter. And as soon as I hit enter, you do see that there is something on the screen that comes back. So it appears that when we hit enter, we are temporarily dropped into a shell, and it says MSH. This is a little difficult because the logs are continuing to be printed out to the screen. So while we do have a shell, it's kind of hard to function inside of this shell because we continuously get those logs back, interrupting what we are trying to type in. But it is a great indication that we are doing everything right. And from this point, you could just basically play around and see what else you can do with this. I noticed that if I tab a couple of times, I get almost like a mini help menu that pops up, giving us different options, such as write MAC address, or reboot, or write device address. And we have some options that are being referred to as W_2I and W_2S. So just to test this out, I want to see what happens if I type in the reboot command inside of this very limited shell. Not sure if that actually rebooted or not. It appears that it did quickly reboot. Let's see if we can interact with the write MAC address. So it's very hard to see because that output continues to get generated to the screen, but it does appear that we also have some sort of tab completion. But it's very hard to interact with this in this manner. I'm pretty satisfied at this point with the results that we have. The main point of all of this is really not to belabor the whole point of actually accessing the device. The focus for me in this video is actually on the tool and how useful this is. When you are done with Minicom, to exit Minicom, it's pretty simple. You just do Control A and then X, and we're going to do yes to leave Minicom. Now if I run ls, I have a file called camera.txt, so I'm going to do wc-l on that file to tell me how many lines exist inside of this file, and we have a little over 3,000 lines. I'm going to open up the file using my text editor of choice, which is going to be Nano, and we're going to quickly take a look at the contents of this file. So this is very, very good stuff. One of the first things that we see is that this is using something called the Thread operating system. The last build was on September 5th of 2023. Appears to be version 3.1.0. Here's some information pertaining to the Wi-Fi access point. I'm going to assume that this is how you connect to this camera. So we have a SSID of NAXCLOW or NAXCLO. There is a key here on the back end, and this is referred to as Wi-Fi Easy Join. Okay, so I don't want to spend too much time on that, but definitely an interesting read. Okay, so for the next demo, I have a Belkin router. Purchased this router for $5 from a thrift store. The first thing that I'm going to do is I'm going to use my multimeter. I'm going to put it into continuity mode, and I need to find the ground pad on the multimeter that I am using. It's a very inexpensive multimeter, which is another word for cheap. To put it into continuity mode, that is the part of the dial that I switch it to. And to test to make sure that it is in continuity mode, it's pretty simple. I'm just going to take the two test leads and I'm going to touch them together. When I hear that noise, I know that it's in continuity mode. So the first thing that I want to do is find that ground pad on the router. I want to take note that the router is not plugged in. I will plug it in here momentarily, but to find the ground pin, you do not need to power the router on. I'm going to try to zoom in with this camera a little bit. I'm recording from different angles, so there's a lot going on right here. You can see that one of those pads has an arrow or a triangle pointing to it, and that could mean one of two things. That could be trying to indicate to us that it is the ground pad or that it's the VCC or the power. I'm going to take a guess and say it's the VCC and not the ground, but we're just going to go through each one of these. There's this big area that is encased in metal right here, a shield. It's probably a good area to use. So the first thing that I actually do is I'm going to make sure that this is suitable for using as ground, and I'll actually touch both test leads to it, and I hear that sound, so I know that that's going to work for me. The next thing that I will do is I'm going to use the black test lead and touch it to the metal shield. I am going to go down the row of pads and determine which one is ground. So I'll touch that first one. I don't hear anything. Touch the second one. I don't hear anything. Touch the third one. Nothing. Finally, there's the fourth one. So I now know that that fourth pad, that last pad, is the ground. That's the first step. Once I've found the ground pad, the next step for me is going to be to figure out which one is the TX pin. And I probably didn't explain this as good as I could have in the previous demo. So let me try to do a better job in this one. With my PCBite probes, I've color-coded them. I have the one with the blue test wire connected to the RX pin on my USB to TTL adapter. So I'm calling this the RX test lead. And in actuality, what that means is the RX goes to the TX and the TX goes to the RX. So if this is the RX on my adapter, that means that the pad that this is going to go to on the board is going to be the TX. So the TX pad on the board is going to be transmitting the data to the RX pin on my adapter, and I should see that output on the screen. After finding the ground pad, the next thing that I want to do is find the TX pad on the router that is going to send data back to the RX pin on my adapter and print it to the screen. So I'll go ahead and connect that to ground. So you can see I just push down and just let go, and it stays right there in position. So we know that it's not going to be this pad with the triangle pointing to it. Can guarantee that that's the VCC pad. So it's going to be one of these two pads. And while you can determine which one is the TX and which one is the RX by powering the device up and taking a measurement, taking a reading of the voltage using the multimeter, it's not able to give me a very good reading like I would want. So I'm going to do this in a simple way, and that's just going to be by trial and error. I'm going to try the first pad, and if it doesn't work, then I'll try the next pad. So before I actually do that, over here on my Kali Linux box, I am going to want to start up Minicom. So I previously created a IoT directory, and in my first demo we have the camera.txt file that we created. Now for this one, same thing, I'm going to do Minicom with sudo privileges. So I'll run the command sudo Minicom. Same baud rate, I'm going to do -b 115200. I'm going to do a capture file with a capital C, and I'm going to call the capture file router.txt. We're going to do -d/dev/tty USB 0. And if you're wondering where I got that from, once again, that was from running a dmessage and plugging the USB to TTL adapter into my laptop and seeing where in my system it was registered. So I'll go ahead and hit enter. Now that we have Minicom up and running, I'm going to come back over to my my Belkin router here, and I am going to just pick one of these pads. I'm going to connect the RX from my USB to TTL adapter to one of these pads. And even though I have not powered the device up, I can actually see some gibberish being printed to the screen on my Kali Linux machine. So that's a good indicator. All right, so that looks like that is good. Try to give you a little close up there of what that looks like. A little hard to see, but that should work. Okay, so let's go ahead and power up the router. Alright, so it's been powered up for a few seconds now, and I'm not getting anything on the screen. I'm not seeing any output. So what I will do next is I will try the next pad. I'm not even going to power cycle it. I'm just going to leave it running, and I'm going to switch to the next pad and see if we get any output. And as you can see, we're now getting a little bit of output. It does make sense. You can read it. It's readable. So that is a great indication, and I'm glad that this worked out the way it did. So you can get an idea of what it might look like if you have the RX and the TX reversed. So I was getting output on the screen. It just didn't make any sense. It almost looked like maybe it was encrypted. But when I switched to that next pad, we got some human readable output. So I'm going to assume that I am using the right pad for the RX on my adapter, and that this is the TX pad on the router, which is what I want. I'm going to double check by power cycling it and seeing if we get some logs generated on the computer here. And we do. Immediately, we can see some information such as the IP address, the MAC address, and we are getting a plentiful amount of logs generated, and the output is on the screen. So this is wonderful. This is exactly what we would hope to see. So we have correctly identified the TX pad on the router, and we are seeing output on the screen of our machine. If I try to interact with it by hitting enter, nothing is going to happen, and that is obviously because we do not have the TX pin on our adapter connected to the RX pad on the router yet, so we can't transmit data. So that'll be the next step. And now, by process of elimination, we know that the last available pad, other than the one with the triangle pointing to it, is clearly going to be the pad that we need. So I'm going to power off the router. For me, the color that is coinciding with TX on my adapter is yellow. So I'm connecting the TX test lead from my USB to TTL adapter to the RX pad on the router. And it's going to be a little tight, so I'm going to have to move some stuff around a little bit. Everything should be ready to go. I'm going to exit out of Minicom and start it back up again. To exit out of Minicom, you do Control A and then X. And we will hit enter for yes. I'm going to remove the router.txt file, and we're going to start over. All right, here we go. Let's go ahead and power up the router. And we can immediately see output being generated on the screen. This is all being saved to our router.txt file. Now I should be able to interact and send data to the device. Let's see if we can. I'll go ahead and hit enter. And we are presented with something called console mode. So this is a little bit unique. Typically when doing this, we might be immediately dropped into a root shell on the device, but that is not the case with this particular device. We are given something called console mode. I've never actually seen this before. This is a little different and also interesting at the same time. So it presents us with two different options, incredibly basic. One is what I'm doing now, which is hit enter to show this help, and the other one is shift plus 0 to enable debug mode. So let's go ahead and see if that works. We're going to do shift and 0, and it is now running console debug mode. I'm going to give it a few seconds to see if any additional output is printed to the screen, and I don't see anything happening, so let me go ahead and hit enter. See if we, oh, there we go. Very nice, very nice. So now when I hit enter, I am presented with this console debug menu, and over here on the left hand side we have the numbers 1 through 8, and then we have A, B, C, D, E, F, G, and then P, S, W, X, and a question mark. This is very interesting. I've never seen this before, so I'm very excited about this and just very interested to see what we can do. I'm not going to spend too much time on it. We'll probably make a separate video diving deeper into this, but see if we can interact with some of these entries in this menu. So number 8 appears to have something to do with the memory. So let me go ahead and hit 8. And we do get some information back. Does some sort of memory check, tells us the free memory and the allocated memory. Let's do S for system. So when I hit S, I'm now presented with a sub menu, and we can dump the kernel with 9. So let's go ahead and see what happens with that. So I hit 9 to dump the kernel, and it does in fact dump the kernel. This is very good. This is very, very good. We go ahead and hit enter again, and it brings up that sub menu so we can show the DNS table with 5. We could use this information to do all sorts of interesting things. Number 4 will show the ARP table. Number 3 will show the routing table. So I will wrap this up. I'm going to exit Minicom. I'll do Control A and X and hit enter. Now back inside of the IoT directory, we're going to have a file called router.txt. I'm going to do a word count on that file, and it is a little over 1,800 lines. Quickly open it up and we'll take a look at it. Definitely a nice amount of information that we have from this. So it appears that it is using the Arcadian bootloader version .14. We could press the space bar to cancel startup. Maybe that would drop us into a root shell. We'll have to try that again. Here's the serial number, the hardware version, the boot version. We have a pin right here. I'm going to take a guess and say that is for WPS, and that's probably some sort of function name for the WPS pin, and this is definitely the pin number. There is the MAC address. We have some memory addresses, UUIDs, and here's where we enter the console mode. This is where we dump the kernel, and you get the point. So a lot of information that we have been able to get from this. And real quick, before I end this demo, I'm going to see if it will drop me into a root shell, because I did notice in those logs that it said something about hitting the space bar upon startup. So I'm going to rerun Minicom, but this time I'm not going to do a capture file. And I'm going to power cycle the device, and I'm going to press the space bar as soon as I power the device back on. And it appears that it did in fact work. Oh, this is great. This is very, very, very cool. So it did work. The startup was canceled, and I am in fact dropped into a shell. And we only know that because we were able to generate these logs upon the booting of the device. By parsing through those logs, we were able to determine that by hitting the space bar upon the boot up of the device, that we could be dropped into a shell. And we are dropped into a shell. And if I do ls, we do not have the ls command, but it does show us available commands. We have the show command, nvram command, the reboot command, flash, go, boot, load, save, param, ifconfig, and help. This is wonderful. This has been a great learning experience. I was only able to do this because of these PCBite probes. If it weren't for the PCBite probes, this would have continued to sit on my desk because of the fact that soldering for me is a barrier to entry. This is why, for me, I am going to say that the most important tool in my arsenal of tools pertaining to hardware hacking or hardware reverse engineering, hands down, are going to be my PCBite probes. If you made it to this point in the video, thank you so much for watching. If you haven't done so already, please subscribe to the channel, like the video, post a positive comment, and as always,
stay fresh.
We'll see you in the next one.